These notes will help you use equations in a new way, and you need this skill not just for AP Physics or for a college physics class, but a lot of science and engineering and math is done using this technique, especially when you're on the cutting edge, when you're doing a new research into something that's never been studied before. You have to use this technique. For example, Newton used it in coming up with his law of universal gravitation because he did not know the value of capital G. He could not just plug numbers into the equation he was proposing. He had to look at change. And specifically, we're not looking at change as in adding or subtracting. We're looking at changes in multiplying and dividing. So I call this equations and multiplicative change. And I think it'll become clear what you have to be able to do through, through these notes. We're going to start with a simple example. Here's our equation, b equals 10a squared. And you're given it the initial value of a is 1. So as always, when you see these blanks, you should pause the video every time and see if you can get the right answer before I tell it to you. So bi would be 10. All right, now, what we talk about next is not necessarily what the new value of a is or what we add to the old value. We're not looking at delta a. That would be an addition. We're looking at taking that initial a and multiply it by a factor. And here we'll pick a really simple factor of 2. So the final a is 2. You write down what the final b is. And of course, it's 40. Now look at what happened to b. As you would expect, it increased. But look, here's how we should look at this increase. Don't look at it as adding 30 because we're talking about multiplicative change. We multiplied a by 2. What did you multiply b by in order to go from 10 to 40? And of course, that's 4. Okay? Now look at this case. We'll start with the same ai, so we're starting with the same bi. Now we're going to multiply a by 3. So the new a is 3. What's the new b? And of course, it's 90. Look at the change. Okay? We multiplied a by 3, but we didn't multiply b by 3. The result is not that b gets multiplied by 3. The result is that b gets multiplied by 9. Why is this? Well, it's all traced to that exponent right there. The exponent is a positive 2. So in other words, you can think of this as 10 times a times a. And this is how I explained it to myself when I first learned this. That really means a times a. So if you double the value of a, each of these gets doubled. So you have 2 times 2 multiplied by 4. If you triple the value of a, each of these gets tripled. So it's 3 times 3. An extra 3 and an extra 3 get inserted into this side that weren't there before, and 3 times 3 is 9. Okay? It's a really good idea if you're having any trouble with this and you're explaining it to yourself to make a t-table out of all this. So you go through and you should do it. I'm going to do that. Of course, this is 10, okay, then 40, 90, 160, 250. Okay, I'll show you what this can do for you. You can see what we already have done. If you double a from 1 to 2, b quadruples. If you triple a from 1 to 3, b gets multiplied by 9. Multiplied by 3 squared, 9, not just 3. But you can also start anywhere you want and use the same approach. And remember, we're not adding. We're not going from 2 to 3 and adding. Although you could do that. That would be multiplying by 1.5. But we'll keep it simple and use integers. So if you start with a equals 2 and double it, multiply by 2, look what happens to b. Again, it gets 4 times bigger. If you start with a equals 2 and multiply a by 3, we expect b to get 9 times bigger, and it does. And then finally, if you start with a equals 2 and multiply it by 4, going from 2 to 8, we expect b to get 16 times bigger, and you can check that and verify that it does. A table like this can also help you because you can start somewhere else. Excuse me, you could start with 3 and double it to 6, and look what happens. It does what it's supposed to do. Start with 4 and double it to 8. You can see the correct thing happens. So look at our conclusion here. For this particular equation, if you multiply a by n, then b gets multiplied by what? By n squared. That's only for this particular equation. It's not some general rule, of course. Okay, now we'll do another equation. Very similar, except now the exponent is a positive 3. So let's go ahead and fill in the blanks. Given that an initial a is 1, bi would be 10. Now multiply a by 2. In other words, double it to 2. So our final a is 2. what's the final b? And of course it's 80. Look at what happened. We're not talking about what we added to b, we're talking about what we multiplied the initial b by. The factor of multiplication here was 8. Why is it 8? Because this is like 10a times a times a. So each of these a's got doubled. 2 times 2 times 2 is 8. 2 cubed. Okay? All right, the factor that you changed a by goes here, replaces the a, and the exponent is taken from the equation, 2 to the third. Now look at this. The way it's phrased here is more compact. Less information is given, and this is the way it could be phrased on a test or in real life. I don't even give you the initial a. I don't say it's a 1, although you could certainly assume it's a 1 and make the problem easier for yourself. But all it says is you multiply the old a by 10. What happens to b? And look at the way that's written. Fewer words. Here's how you say, in fact, we could cross all of this out and just say this is given. Given. New a equals 10 times old a. So the new b equals what times the old b? And you look up here, well, a is raised to the third, a is cubed, so you would cube 10 and you get 1,000, or 10 cubed. So if you make a 10 times bigger, b will get 1,000 times bigger. All right, that's a more compact way. This is the way it's most commonly phrased, something like this. No values are actually, notice it, at no time do we actually give any of the values for a or b. No particular, all we talk about is if we change a by this factor, b will change by what factor. In this example, you have a dependent variable y that depends on 1, 2, 3, 4, 5 independent variables, all in capital letters, and that k is a constant. This is the kind of thing you would see in a college equation, especially in more advanced college class, and especially in something like graduate school or a professional school. You'll have functions where the dependent variable depends on several different independent variables. This is what Newton was facing when he did the law of universal gravitation, because he did not know capital G, right? It was the force of gravity equals capital G m1 m2 over the distance squared. 1, 2, 3 independent variables, 1 dependent variable, and he did not know the mass of the Earth or the value of capital G. So there are two values in this that he didn't know. So he could not work this out by plugging in numbers. So what he had to do was look at multiplicative changes. If the distance got 3 times bigger, he would find that the force of gravity got 9 times smaller, and so forth. And that's how we verified that this equation was the correct one. Okay, so look at the way I've set this up. We'll go one variable at a time and ask what happens if we double it. If we double a, what will happen to y? And we'll write that as a single factor. New y equals some factor times the old y. And what's implied here is that everything else is being held constant. So for this first line, we're going to make a twice as big, but hold the other 4 letters constant, and k is a constant. So everything else is held constant, so it's like one big number. And all we're going to do is change one letter. So we make a twice as big. You figure out what goes here. What happens to y? Well, because a is linear, there's a 1 implied there. The same thing happens. So if we make a twice as big, it puts a single 2 on this side, which doubles this side, so y has to double to keep it in balance. Now let's look at b. b is cubed, b to the third. And so if we double b, that's b times b times b, so y gets 8 times bigger. Now let's look at c. Oh, that's rooted, but that shouldn't bother you. That's just c to the 1/2. So it's the same thing you did here when it's b to the third. We doubled b, so we use 2 to the third is 8. We double c, so we use 2 to the 1/2. So 2 to the 1/2, or square root of 2. And if you want to get a feeling for what that is as a factor, it's not a bad idea to memorize the square root of 2 and the square root of 3 at least to 2 digits, 2 significant figures. I have it memorized to 4. That's what we did. 1.414 before there were calculators. 1.414, if you're into European history, it's also the Council of Constance, one of those ecumenical councils, the church councils. So 1414, 1.414, and that makes sense. It's bigger than 1, but it's smaller than 2. So if we make c get bigger, we expect y to get bigger. But if we double c, we don't expect y to double, because that's what it would do if it were just c to the 1. But it's c to the 1/2. So what we do is we expect a number here that's between 1 and 2, and we get it. Okay, now let's look at d. There was nothing like this in the previous 2 examples. D is in the bottom. It's in the denominator. So that means if D increases, then what happens to y? Well, this is a fraction. Imagine holding everything else constant. So it's kind of like a big 1. And you have 1 over d squared. And as d gets bigger and bigger, y has to get smaller and smaller and smaller. Some people will say this as dividing by, but the way I've structured this, we have to put a factor in here. But if we expect, when we double d, we expect y to get smaller, that means our factor is going to be what? What can you say about that factor? It's going to be less than 1. Okay, so if you treat everything else like a 1 there, then it's like you have 1 over d squared, or d to the negative 2. So that's the way to think of it. So we're doubling it, so we have 2 to the negative 2, or 1/4. That's the factor that goes in here. It's perfectly okay to say y gets 4 times smaller, as long as you don't get confused. Saying 4 times smaller, or you could say y is divided by 4. That means the same thing as multiplying by 1/4. All right, let's look at the final one. E to the fourth, but in the denominator. So this is like e to the negative 4. And so if we double e, our factor of multiplication is going to be 2 to the negative 4. So 1 over 2 to the fourth, which is 1/16. That's our factor that goes in here. Another way is to say that y is divided by 16, or to say y is 16 times smaller. Those are all correct. All right, and finally, I'll show you how we would use this technique to do that lab. I wanted you to try that lab on your own. I saw a lot of good reasoning on it, but this is probably the most compact and most straightforward way to deal with it, and it's a way that enables you to look at not just the case of doubling, but any case, because you're not plugging in numbers, you're looking at behavior or trends. You've seen all this, and you can pause the video, so I'm going to go pretty fast. We measured time, and we doubled the mass. So we want an equation with those two things, time and mass. But there is no single equation given to you with time and mass in it, so we had to use two things. This equation for speed, and this equation for turbulent air resistance when you're at terminal velocity. That should all be familiar with you, so I want to explain it. I'm putting the variables in red. What I did was I nested, first I dropped one coffee filter, then I nested two of them together, so 2 fell, so I doubled the mass, so I was controlling the mass, and I was measuring the time. And the terminal velocity was different in the two cases, but I couldn't measure that because I never told you the distance. So we controlled m, and we measured t. Now, students often think that time is always the independent variable, and that's completely false. In this experiment, we changed the m. We chose what was going to happen to m. You never actually knew what m was. We did not put the coffee filter on a scale, but you know that we doubled it. And then we measured t. So we think of the time as depending on what we did to m. T is the dependent variable. M is the independent variable. If you take these, combine them, and solve for the dependent variable, you get this. And once again, the variables are in red. The constants are in black. So this whole thing in here is like one big constant. You could call it like C for a constant. This and this are what show you the really important relationship here. T goes as 1 over the square root of m. That's how scientists talk. T goes as 1 over the square root of m. T is inversely proportional to the square root of m. Okay, now use the analysis we developed on the previous pages. The new m was twice the old one because I put 2 coffee filters together and let them drop. I doubled the m. So what should happen to the t? Well, based on the analysis we did before, you look at this as m with an exponent. What would that exponent be? Well, we got everything going on here. Negative exponent and a fractional exponent. So if we double the m, the factor of multiplication on the t is going to be 2 to the negative 1/2, or 1 over the square root of 2. You should have a feel for whether that's bigger or smaller than 1, and roughly what it is, and you can do that. Remember, we know the square root of 2 if we have it memorized, and this is why that math teacher, I forget her name, but the math teacher that works here, Ms. whatever, that's why she teaches you to rationalize the denominator so you can do this kind of thing in your head. 1.414, Jacobson, that's her name. Okay, equals 0.7071. So when I was in high school, we would see that so often we'd have it memorized, right? Because it's the sine and cosine of 45 degrees. All right, so that's our multiplying factor, 0.7071. Notice it's less than 1, so it's going to mean that final t is smaller than initial t. Well, here was the initial t I measured. You multiply it by 0.7071, and I think you get 0.52. So that's the predicted. If the flow is turbulent, it predicts, this analysis predicts that the time with 2 coffee filters will be 0.52. I actually measured 0.53 seconds, and this equation gave an almost perfect prediction for the second time. The other equation for smooth flow gave a prediction that was way off. Certainly much more wrong, bigger error than this was. And that's how we can confirm it. This may seem like a lot, but it really all reduces to this relationship between the dependent variable and the independent variable. And once we know that, we can predict what will happen for any change to m. For example, if I make m 25 times bigger, I would expect t to get 5 times smaller. And that's why this is a lot better than setting up in real life, in a real lab or in real research. This is a lot better. This is a better technique than trying to set up proportions and plugging in specific values. Because any scientist can look at this and talk about the trends.